Today, let's have a basic idea about transistor, its construction and its working. The term transistor indicates transfer resistance. It transfers signals from a low resistance region to a high resistance region. There are two types of transistors, NPN transistor and PNP transistor. A transistor is a combination of two diodes. Here we can see a PN junction diode, and here also there is a PN junction diode. That means we can define this transistor as a P-type semiconductor is sandwiched between two N-type semiconductors. Usually for any circuits, we'll be having two terminals for the input and two terminals for the output. But here for a transistor, there is something special, that is, one terminal is kept common for the input and the output. So for a transistor, there are three terminals: emitter, base, and collector. This is the symbol of an NPN transistor. The common terminal is set as base, collector and emitter in either sides. And for representing the emitter, we are using an arrow here. For representing a PNP transistor, this arrow direction will be reversed. Electrons are the majority charge carriers in an NPN transistor. Usually, NPN transistors are widely used. This is because of the reason that the electrons are having greater mobility than the holes. According to Newton's second law, force is equal to mass into acceleration. We can see acceleration and mass are inversely proportional. An electron has got a lower mass. Thus, it indicates that it can move with a greater acceleration. So, NPN transistors are mostly preferred than PNP transistors. Let's have a look onto the construction of an NPN transistor. This will be the emitter, base, and the collector. The size of the base is less when compared with the other two segments. Emitter is having a greater size, and the collector is having the greatest size when compared with the other two. And for these three layers, the doping levels are also different. The base section will be very lightly doped. The doping of the collector will be very moderate when compared with the other two layers. And higher level of doping is seen with this emitter section. This is because of the reason that the emitter has to emit, so higher level of doping is given. The collector has to collect electrons, so it is made more spacious. By comparing, we can say that the base is having lower size and lower level of doping, and for an emitter, the size is kept moderate, that is, greater than base but smaller than collector. But it is having a higher level of doping. And for a collector, the size is kept very high, but the doping level is kept moderate, that is, greater than base but less than emitter. Now we'll be discussing how to activate a transistor. This condition is maintained to activate a transistor. EFCR. E indicates emitter junction and F indicates forward bias. This means that emitter junction should be forward biased and the collector junction should be reverse biased. We are familiar with the connection forward bias and reverse bias. For forward biasing, we have to keep this in mind: N to N and P to P. That means the N region should be connected to the negative terminal of the supply voltage and the P region should be connected to the positive terminal of the supply voltage. And for the reverse bias condition, the N region should be connected to the positive terminal and the P region should be connected to the negative terminal. Now we will assign the polarities for these supply voltages. The emitter junction should be forward biased. That means this N region should be connected to the negative terminal of the supply voltage, and the collector junction should be reverse biased. That means the N region should be connected to the positive terminal of the battery. Let's have a look what all changes are going to happen to this transistor when it is connected to these supply voltages. As this junction is forward biased, it will be having a narrow depletion layer. But this junction is reverse biased, so it will be having a wider depletion layer. Now we are going to consider the effect of this voltage, the voltage at emitter VEE. The negative polarity offered will be experienced at this position. We know the electrons will get repelled when it faces a negative voltage. Thus the electrons get repelled to the other side. Some of the electrons could manage to occupy the space provided by these holes. What happens to the rest of the electrons? It gets attracted to the positive terminal of the supply voltage of collector VCC. So, at the emitter region, electrons were moving in this direction in order to complete the path from negative to positive. Thus, according to the sign convention, the emitter current IE can be represented from positive to negative. Now, what happens to these electron hole pairs formed here? With the effect of this positive terminal, the electrons will get sufficient energy to break the bond and will manage to flow towards the positive terminal. By this electron movement, there will be a base current and the direction will be in the opposite direction. Similarly, there is one more current, IC, of the collector current. By the effect of this positive terminal, the electrons from the collector side will be traveling towards the positive terminal of VCC, thereby constituting the collector current IC, which can be shown in the opposite direction. By applying the Kirchhoff's current law at this junction, we can relate all these currents. According to the law, the sum of currents entering the junction will be equal to the sum of currents leaving that junction. So the relation for the current can be obtained as IE is equal to IB plus IC. The emitter current will be a combination of the base current and the collector current. This is the basic working principle of a transistor, which is widely used in almost all the electronic circuits. Thank you for watching.